This video goes through the differentiation of x to the n. Now we've already come up with this rule when we were differentiating by first principles. So we know the rule, now we're going to apply it. Okay, so first of all, what are we starting with? Are we starting with f of x, the function of x, or are we starting with y? If we're starting with the function of x or the f of x, our notation for gradient is f prime of x. So you can see that little dash there. Now we've already spoken about that too. If we're starting with y, then our notation is dy dx, that change in y over change in x, and that comes back to our Leibniz notation, which we've already looked at as well, delta y over delta x, change in y over change in x. Now, on that, remember the key words we're looking at when we know we need to find the derivative. So rate of change, gradient at a point, instantaneous rate of change, gradient of the tangent at the point. Those are the words, when we see those, we have to be thinking we're going to be differentiating. Now, our rule, which we came up with last lesson when we were differentiating by first principles, is we times the coefficient of x by n. So we have a times n, write our x, and then we decrease our power by 1. And of course, that's the same if we're starting with y. It's just that we've got that dy dx out the front. So let's apply that. We have y equals, so dy dx is going to be, we bring the 5 out the front. There's a 1 out the front of the x, so it's 5x, decrease my power by 1, 5 minus 1. Minus 2 times 3 is 6, x to the 3 minus 1. We have no x with the 2, so that's gone. So we've now got 5x to the 4 minus 6x squared. Now you don't need to show this intermediate step. I'm only doing that as I'm introducing the rule. So that is our gradient function. So what that means is for the curve x to the 5 minus 2x cubed plus 2, my gradient curve is given by 5x to the 4 minus 6x squared. So I could find the gradient at any point on that curve by just plugging in the coordinate into that equation. So if I wanted to know my gradient at x equals 1, I'd plug it into dy dx. I'd go 5 times 1 is 5, minus 6 times 1 is 6, 5 minus 6 is negative 1. If I wanted to know the gradient at 0, x equals 0, I'd plug it in and I get 0. So this is what we call a gradient function. We can find the derivative at any point now. Moving on to our f of x, it's going to be f prime of x is equal to 4 times 3 is 12, x, 3 minus 1 is 2, minus 6 times 2 is 12, x, 2 minus 1 is 1, plus, now there's a 1 in front of the x, so it's plus 1. We could write x to the 1 minus 1 is 0, so it'd be x to the 0, which is 1. So that is our gradient function. Pause the video, have a go at the next one on your own. Now we have the function of g, so my derivative is g prime x. So it's going to be 12 times 4 is 48, x, 4 minus 1 is 3. Minus 3 threes are 9, x, 3 minus 1 is 2. Plus 7 times 2 is 14, x, 2 minus 1 is 1. Plus, and then we have that 5 on the end. If you're given brackets, you're going to have to expand the brackets at this point in time until you learn a shortcut. So here we have x squared plus 6x plus 9. If you forget how to expand your brackets, then put them in full. So x plus 3 times x plus 3, x times x is x squared, x times 3 is 3x, 3 times x is 3x. So you've got 2 lots of 3x, which is a 6x. 3 times 3 is 9. So now I've expanded those brackets, I can now differentiate. So my dy dx, bring the 2 out the front, x plus 6. With the next one, what we have to do is get rid of that denominator. So we split. We've got x squared over x plus 3x over x. X squared over x is x plus 3x over x is 3. So my derivative is f prime x. Derivative of x is 1. For the next one, I need to expand my brackets. So 2t squared is 4t squared, minus 2 lots of 2t is minus 4t, negative 1 squared is plus 1, then t plus 2. Now I have to expand these brackets. So I've got 4t cubed plus 8t squared minus 4t squared minus 8t plus t plus 2. Collect like terms, you got 4t cubed, 8t squared minus 4t squared is plus 4t squared, minus 8t plus t is minus 7t plus 2. Now I do differentiate. Now it's dz dt. We're differentiating z in respect to t. So 4 3s are 12, so 12t, 3 minus 1 is 2, plus 4 times 2 is 8t, and then we have minus 7. So you see here with our notation, it's a derivative of what's in front, the change in z over the derivative of my independent variable, which is t dt. So the change in z over the change in t dz dt. Other things to take note of now, it's not specifically in the subject matter, but if you have y equals 3 over x to the 4, then what you're going to have to do with that is use your index rules and bring that x to the top to make it negative 4. So my dy dx is going to be 3 times negative 4 is negative 12x. Negative 4 minus 1 is negative 5. So be careful with that. Then to put it back in as a fraction, that x to the negative 5 goes to the bottom to make it positive. If I had y equals the cubed root of x, that would become x to the third. So again, we're using our index rules. So dy dx would be, we'd bring the third out the front, x, 1/3 minus 1 is negative 2/3. To put that back in terms of a fraction with a positive power, I'd have 1 over 3x to the 2 over 3, which I could rewrite as 1 over 3 the cubed root of x squared. So that's bringing in your index laws. So just be careful of that. It's not specifically in the subject matter, but you should know how to do it. It would definitely be considered a unfamiliar question.